If you're building an AI integrated application that needs vector search, you'll quickly run into an important question. Should we use vector search built into the database systems we already run, or deploy a dedicated vector database? Choose wrong, and you might be dealing with performance issues from day one, or spending weeks building database systems you didn't actually need. In this video, you'll learn the real differences between traditional and vector databases for vector search. And stick around to the end for a practical framework to help you decide which one is right for you. But first, let's quickly revisit what vector search actually is. At its core, vector search is pretty simple. Using some Python code to demonstrate, you just need an embedding model, a persistent store for your embeddings, in this case, just a JSON file, an in-memory index, and then searching is just converting the query into an embedding, iterating through the index to find the closest matches, looking up the original text, and returning the results. Now, obviously, this is oversimplified, but the point of this demo is to show that implementing vector search isn't the hard part. Scalability is the hard part. And if you're deploying at the edge or on-prem without the luxury of elastic compute, efficiency at scale is even more crucial. So understanding the scale that you're operating at now and where you'll be in 18 months is the clearest signal for whether an existing database system is enough or whether you need a vector database. But before we get into scale, we need to clear up a common misconception about traditional versus vector databases, what I call the feature gap myth. It's understandable if you're thinking that vector databases must have far more advanced search features than something like the pgvector extension for Postgres. That assumption, though, is mostly wrong. Modern databases with vector search support, such as Postgres, MongoDB, Redis, and Elasticsearch, can all use AND indexes, apply sophisticated filtering, and support hybrid search that blends vector similarity with keyword matches. Feature gaps are not typically the deciding factors. There are nuances, of course. So, for example, BM25 indexes are the default for keyword scoring in hybrid search across most vector databases, but Postgres does require an additional extension for this. The key point is that vector databases aren't typically chosen because they offer better search features. They're chosen because they're purpose-built to efficiently scale to hundreds of millions or even billions of vectors. Which raises the question, what's your vector search scale? Most people assume vector search scale just means the number of vectors, but that's only part of the picture. You can approximate your raw vector storage size by taking the vector count and multiplying it by the embedding dimensions and vector value precision. Storage then determines your index size, and index size determines your memory requirements. But even index size is only one dimension of scale. A more complete way to think about this is that there are four sources of pressure on your vector search infrastructure. Vector storage pressure. How large is your embedding footprint? Not just vector count, but also dimensions and precision. Query volume pressure. The query per second volume, available compute, index size, and whether you're running pure vector search or hybrid search all factor into the infrastructure needed to hit your latency targets. Index maintenance pressure. The index type, how frequently data is ingested, and in what volumes determine the maintenance pressure on your index. This means compute and memory allocation also needs to account for index maintenance, not just holding the index in memory. Optimization pressure. When query latency starts creeping up, what tuning and optimization options do you have, and how far will they get you? These pressures affect both traditional and vector databases, but with traditional databases, the cracks usually appear earlier, especially for edge and on-prem deployments that don't have the luxury of elastic compute. So with that in mind, let's look at some edge and on-prem considerations. Implementing vector search at the edge or on-prem is usually driven by infrastructure requirements, such as data locality and cost predictability compared to usage-based cloud pricing. The trade-off is that on-prem infrastructure is typically more constrained. You don't have the option of quickly scaling compute to handle spikes in query volume or indexing demands, which means capacity planning and vector search efficiency become much more important from the start. On-prem also means the performance you can squeeze out of your existing database systems depends heavily on your team's expertise. And without that expertise, the move to a vector database may need to happen sooner. Optimizations come in many forms, but for now, I want to highlight two key optimizations that can have a huge impact on performance, index size, and operational overhead, regardless of the database or deployment environment. Reducing embedding dimensions and reducing vector precision. What many teams discover is that the initial values chosen are often more than they actually need. Here's a concrete example of how much storage you can save. Say you're storing 10 million vectors at 768 dimensions using 32-bit floats. That's roughly 30 gigabytes of raw embeddings. You could cut the embedding dimensionality in half, say from 768 to 384, either by choosing a smaller embedding model or one that supports multiple dimensions using Matroshka training. Then, by dropping the precision of each vector value from 32-bit to 16-bit, storage falls to roughly 7.5 gigabytes. When testing optimizations that reduce dimensionality or precision, make sure you run them against a proper set of retrieval evals, not just a handful of ad hoc queries, to check that retrieval quality hasn't degraded. Now, we've covered a ton in this video, so I want to leave you with a set of high-level questions you can use to guide your evaluation process. Cloud or on-prem? This sets your compute constraints and the range of optimization options available. Run evals before estimating scale. Test your embedding model, dimensions, and value precision using evaluations on a representative subset of your data, as you may need less than you think. Estimate your vector count and storage. This largely depends on your chunking strategy. For text workloads, a good starting point is around 400 tokens per chunk, roughly 250 to 300 words, which gives you an estimate of how many vectors you'll generate from your dataset. Estimate CPU and RAM requirements. You'll need memory to hold the index, compute for similarity search, and additional compute and memory for index maintenance. Your estimated vector storage size gives you a starting point for all three. Assess existing infrastructure headroom. Combine your RAM estimates with expected query volume and the percentage of vector search relative to existing queries to determine whether your existing database instance has enough headroom, or whether a dedicated instance is needed from the start. Pressure test index maintenance. Ingestion frequency, whether writes are append only or update heavy, and whether indexing must occur immediately all affect the headroom required for index maintenance. Model your query load. Factor in peak QPS and latency requirements to estimate real compute consumption. For example, real near-time search may require optimizations that trade recall for speed, but that's a trade-off you don't want to be making under pressure in production. Once you've worked through those questions, the answers usually place you into one of three buckets. The workload fits comfortably. Your projected vector count, index size, and query load sit well within the headroom of infrastructure you already operate. In that case, starting with an existing database system is the simplest and most practical option. The workload technically fits, but with limited headroom. You could either scale up your infrastructure or evaluate a vector database to see if its indexing and query efficiency justifies the switch. For edge and on-prem deployments, vector database efficiency is more of a deciding factor. The workload exceeds what existing database systems can support. At this point, moving to a vector database becomes the more practical solution. The key takeaway is this: vector databases aren't chosen because they offer superior search features. They're chosen because they solve scalability challenges that traditional databases with vector search support weren't designed to handle. So the real question is whether your vector search scale justifies introducing a dedicated vector database. Thanks for watching, and I'll see you in the next video.